Good evening, sir.
Hello, ma'am. Yeah, ma'am.
Hello, sir. You can start, sir.
Yes, ma'am.
Good evening, sir.
Good evening. Ma'am, make me a host.
Yes, sir. You can continue, sir.
So today will be the last class on this chapter, electrochemistry. Tomorrow we'll start with a new chapter, kinetics, chemical kinetics. We will learn tomorrow. Now, a few of the questions I have to teach you. I've taught you all type of questions. It will be like a revision to you. Few questions we will learn. Cell potential or EMF of the cell. How do you define cell potential or EMF of the cell? It is defined as the difference in potential of two half cells. Of a cell is known as electromotive force or electromotive force of the cell or cell potential. Now you should remember that an electrochemical cell will be made of two half cells. If you remember Daniel's cell, we have zinc electrode and we have copper electrode. Zinc electrode and copper electrode. The zinc electrode and copper electrode are connected through an external wire through voltmeter and internally by means of salt bridge. So each electrode is considered to be a half cell. So zinc electrode is a half cell and copper electrode is also a half cell. Two half cells will give you one complete cell. So what is this EMF? The difference in potential between two half cells is known as electromotive force, EMF of the cell, or it's called a cell potential. Did you understand this? Followed or not? Yeah.
Yes, sir.
Yes. Now, in case of this Daniel's cell, zinc electrode is an anode. Anode is represented by a negative sign. Copper electrode is cathode, represented by positive sign. You know the sign convention. Now, at anode, oxidation takes place. Zinc loses 2 electrons to form Zn2+. These electrons which are formed will move towards copper through the external circuit. At copper, these copper 2+ ions will accept 2 electrons and get reduced to copper. So this is a reaction. This is half cell reaction at zinc electrode and this is half cell reaction at copper electrode. When you add two equations, what we get is, we get zinc plus Cu2 plus giving you Zn2 plus Cu. This is the overall reaction of Daniel's. Now what happens is, electrons flow from anode to cathode. Loss of electron or gain of electron is nothing but change in chemical energy. That change in chemical energy appears as current. So current will flow from cathode to anode. That is what they were represented here. See, anode to cathode, flow of electrons. From anode to cathode, there will be movement of electrons, a flow of electron. Current will flow from cathode to anode. That is what is explained here. Clear with this?
Yes, sir.
And we can also calculate the EMF of the cell or cell potential from the values of electrode potential of two half cells constituting the cell. The following three methods are used. What following three methods? Not following three methods. When oxidation potential of anode and reduction potential of cathode are taken into account, we can calculate the E cell to be E naught cell is equal to electrode potential oxidation minus or plus of what? Electrode potential reduction. Now, this is one of the way of calculating the oxidation potential. So we will learn some of the questions again, and then we'll try to wind up the electrochemistry chapter today, possibly. All right. Now, the first question, what we're going to learn here will be, when electricity is passed or allowed to pass, then which of the following is decomposed? Which of the following is decomposed? They're asking you, amongst the following, which is...
Sir, is it option B, sir? Is it option? So option D, sir.
It's AgNO3, silver nitrate, because this are all these are non-electrolytes. All these are non-electrolytes. They will not decompose when dissolved in water. Therefore, they are non-electrolytes. So silver nitrate will dissociate to form Ag plus and NO3 minus. So this silver nitrate is called as an electrolyte. So silver nitrate will decompose on passing electricity. So the answer for this question is option D. The next question, the amount of ion discharged during electrolysis is not directly proportional to resistance, time, current, electrochemical equivalent. What it is? What's the answer? What's the answer? The amount of ion discharged during electrolysis is not directly proportional to resistance, time, current, electrochemical equivalent. Ajay, Dhanlakshmi, Ritika.
Sir, time, sir.
Very good. It's our wrong answer. Dhanlakshmi.
The chemical equivalent.
Wrong answer. This is based on Faraday's first law. W is equal to Z into I into T. So W is directly proportional to what? Equivalent, electrochemical equivalent. Electrochemical equivalent.
Sir, then it's resistance, sir.
The only option left out is resistance only.
Yes, sir.
So amount of ion discharge is not directly proportional to resistance. See, conductance is the reciprocal of resistance. Remember that. So how much of current you pass, so much of metal will get deposited here. So maybe we can say W is directly proportional to conductance also, but it is reciprocal, it is inversely proportional to resistance. So which is not directly proportional to their asking. Hence the answer for this question is option A. Understood this?
Yes, sir.
Yeah.
Yes, sir.
Next question. The electric charge required to deposit 1 gram equivalent weight of an element is 1 ampere current, 96,500 coulombs per second, charge on 1 mole of the electron, both A and B. What's the answer for this? The electric charge required to deposit
So both A and B.
both A and B.
So option D, sir, both A and B.
Yeah, charge on 1 mole of electron is nothing but 1 Faraday. 1 Faraday is again 96,500 coulombs. So the answer for this question is option D, both A and B. The SI unit of molar conductivity is? The SI unit of molar conductivity is? What's the SI unit of molar conductivity? Siemens
So
centimeter.
option B, sir.
Option?
So option. So option D.
Option D. SI unit is meters. Siemens meter square per mole. So the answer for this question is option D. The SI unit for molar conductivity is Siemens meter square per mole. Correct. That's fine. The next question. See, it's a regular 11th, 12th question also. They can ask you for 1 mark. So you should be in a position to remember that. Now this question we will see. The resistance, I've not given you the options here because it's a lengthy problem. I didn't have time to type the options. So we'll work directly and come out with an answer for this. The resistance of 0.01 normal solution of an electrolyte was found to be 210 ohms at 298 Kelvin. Using a conductivity cell with a cell constant 0.88 centimeter inverse, calculate the specific conductance and equivalent conductance. What is given in the question? They've given you the concentration to be 0.01 normal. They've given you. And also they have given you the resistance to be 210 ohms. 210 ohms. And also if you observe, they've given you the cell constant. Cell constant is length by area. This is called a cell constant. They've given us 0.88 centimeter inverse. They're asking you to calculate specific conductance and they're asking you to calculate equivalent conductance. Now, how do we calculate specific conductance? What is the formula to calculate specific conductance? Specific conductance is represented by letter kappa. It is given by the formula 1 by R into L by A. This is there in the theory we have learned. Specific conductance kappa is equal to conductance into L by A. Conductance is 1 by R, reciprocal of resistance. Because they've given you the resistance is 210, 1 by 210 into cell constant they've given us 0.88. On simplification, the answer what we will get is 4.19 into 10 to the power minus 3 ohm inverse per centimeter inverse. So this is specific conductance. This is specific conductance. Did you follow this part of the problem?
Yes, sir.
What is equivalent conductance? How do you calculate equivalent conductance? Equivalent conductance is given by the formula relation specific conductance into 1000 divided by normality. Concentration we will generally write. Since we are talking about equivalent conductance, it is in terms of normality. Specific conductance we found out now here, 4.19 10 to the power minus 3 into 1000 divided by, they've given you the normality to be 0.01. On simplification, the answer what we will get is 419 ohm inverse centimeter square per equivalence. So the answer, the equivalent conductance is 419 ohm inverse centimeter square per equivalence. Did you follow this?
Yes, sir.
Yes.
Yes,
So these
sir.
are the problems and formulas you please try to remember and follow it up. Sixth question, the specific conductivity of a solution containing 1 gram of anhydrous barium chloride in 200 centimeter cube of the solution has been found to be 0.0058 Siemens centimeter inverse. They've given you the specific conductance, 0.0058 Siemens centimeter inverse. They're asking you to calculate the molar and equivalent conductivity of the solution. And they've given you the molecular mass of barium chloride as 108. Now, you know what is the weight of barium chloride? You have given molecular weight, they've given you the volume. Firstly, you need to calculate the molarity of barium chloride. How do you calculate the molarity of barium chloride? Weight in grams by molecular mass into 1000 divided by volume of the solution. So weight in grams, how much of barium chloride they're giving? They've given barium chloride to be 1 gram. Molecular weight of barium chloride is 208 into 1000. Volume of the solution, what's that volume of the solution? They've given 200. So if you simplify this, the molarity of barium chloride, you will get it as 0.024 molar. This is the molarity of barium chloride. This is the first part of the problem. And what is the normality of barium chloride? We need to calculate normality also because we want equivalent conductivity. So normality of barium chloride is twice the molarity. That is 0.024 into 2. That will be equal to 0.048 normal. Normality we have calculated molarity. Now tell me, how do I calculate the molar conductance? Molar conductance is specific conductance into 1000 divided by molarity. Specific conductance is 0.0058 into 1000 divided by molarity is 0.024. Hence the answer for this will be 241.67 Siemens centimeter square per mole. Likewise, equivalent conductance will be specific conductance into 1000 divided by normality. So it will be 0.0058 into 1000 divided by normality we found to be 0.048. So it will be 120.83 Siemens centimeter square per mole. Per equivalence, this is per equivalence, sorry. Did you follow this? Understood or not? See, if you are not able to know this relation, if you're not able to know this relation, normality we can also calculate it by the formula. Normality is calculated by the formula weight in grams divided by equivalent weight into 1000 by volume. So here it's molecular mass in order to calculate molarity. In order to calculate normality, it is equivalent mass. So how do you calculate equivalent mass of barium chloride? It will be half of this because Ba2 plus. So 208 divided by 2, it will be 104. If you substitute here 1 divided by 104 into 1000 by 200, you will get 0.048. So this is the same formula. Only difference is here it's molecular mass. Here it is equivalent mass. Right? So pay attention. I hope you followed with this.
Yes, sir.
Yeah. Am I not going fast? You're able to follow everybody?
Yes, sir.
Yes, sir.
Yeah. See, the value of mu infinity, that is molar infinite conductance. Infinity, I was not able to type it. I was not able to search it. This also is infinity here. So value of mu infinity for ammonium chloride, sodium hydroxide, sodium chloride are 129.8, 248.1, and 126.4 ohm inverse centimeter square per mole, respectively. Calculate the molar conductance at infinite dilution for ammonium hydroxide. So they're asking you to calculate molar conductance at infinite dilution for ammonium hydroxide. How do I get this? From these data, we need to arrive at ammonium hydroxide. So I can write it is molar conductance of ammonium chloride at infinite dilution plus molar conductance of sodium hydroxide at infinite dilution minus molar conductance of sodium chloride at infinite dilution. What happens? Now this is Na plus Cl minus, Na plus Cl minus, the Na plus OH minus. It's Na plus here, Cl minus. So what happened? This Na plus and this Na plus will get cancelled. This Cl minus and this Cl minus also will get cancelled. What else is left out? We have ammonium and what? OH minus. So we're getting the answer. So what is this? So it'll be 129.8 plus 248.1 minus 126.4. So that will be giving you 251.5 ohm inverse centimeter square per mole. Did you understand how to? This is based on what? Kohl-Rusch's law. This problem is based on Kohl-Rusch's law. Because Kohl-Rusch's law is used to determine the conductance for weak electrolytes. Ammonium hydroxide is a weak electrolyte. It is not a strong electrolyte. So this problem is based on Kohl-Rusch's law. Followed?
Yes, sir.
Yeah. The next problem. Calculate the molar conductance for ammonium hydroxide. The same problem, but little difference. Let's see. Calculate the molar conductance of ammonium hydroxide. Given molar conductance of barium hydroxide, barium chloride, and ammonium chloride are 523.28, 280, and 129.8 ohm inverse centimeter square per mole, respectively. Now they're asking you to calculate the molar conductance of ammonium hydroxide. Now, in order to calculate the molar conductance of ammonium hydroxide, firstly, molar conductance of barium hydroxide is molar conductance of barium ions plus twice the molar conductance of OH minus.
So OH ion, sir.
Yeah, twice.
Yes,
Two
sir.
times, because two barium hydroxides are BaOH twice. So that they have given us 523.28. This will mark it as equation 1. Now, what's the molar conductance of barium chloride? That will be again molar conductance
So
of
molar conductance of barium
plus
plus
twice the molar conductance of what? Cl minus. What they have given us 280.0. This is equation 2. What is molar conductance of ammonium chloride at infinite dilution? Ammonium chloride only, no, they've given, yes, they've given ammonium chloride. It is molar conductance of ammonium ion plus conductance of chloride ion that they've given us 129.80. This is marked as equation 3. Now, what is that? Oh, no space. All right. Now, in order to get the molar conductance of ammonium hydroxide, what are we supposed to do? Equation 3 plus equation 1 divided by 2 plus equation, not plus, here it is minus equation 2 divided by 2. Why I have to divide it by 2? Here you can see there are 2 OH. We don't want 2 OH because in the required is what, only 1 OH. And here also you can see 2 chlorine is there. Therefore, we are dividing it by 2. So what happens now? 129.80 plus of 523, no, that is?
Yes, sir. 523.28.
523.28. 28 divided by 2 minus of, that is 280.0 divided by 2. On simplification, we will get the answer 251.44. The answer will get us 251.44. Hence, the answer for this is 251.44. You understood why I'm dividing it by 2? See, this is again Kohl-Rush's law only. In the previous problem, they have given what? All are monovalent. So we just added these 2 and subtracted here. But here it's divalent ions they've given. Barium is divalent and you give 2 OH minus. Barium is divalent and you give 2 Cl minus. Therefore, we have to divide these values by 2 and then add up with equation 3. This is equation 3 plus equation 1 by 2 minus equation 2 by 3. Just see what happens. Just see what happens. Equation 1 by, you add these equations. That is, here if you add this, equation 3 is ammonium chloride plus barium hydroxide minus what? Barium chloride. Now here, only 1 Cl is required. And we want 1 OH here. Since we have 2 chlorine, this also divided by 2, this also divided by 2. And finally, you will get what? Ba by 2 here. So what you will get, I don't know whether you are able to understand what I'm writing here. So if I divide, you will get what? Where's that gone? Just give me a time. So you will get ammonium chloride plus of Ba 2 by 2 and what? You will get 1 OH minus of, here also you'll get Ba by 2 and you will get 1 Cl. So what happens? This Ba plus Ba by 2 and minus Ba by 2 will get cancelled. This Cl minus and this Cl minus will get cancelled. What else is left out? NH4 plus and what? OH minus. So we are getting the answer. Are you following this? Students, did you follow what I did?
Yes, sir.
The next question. What's that question now? Next. The resistance of one normal solution of salt is 50 ohms. Is 50 ohms. Calculate the equivalent conductance of the solution. Calculate the equivalent conductance of the solution. If 2 platinum electrodes in solution are 2.1 centimeter apart and each having the area 4.2 centimeters square, the resistance of one normal solution of salt is 50 ohms. Calculate the equivalent conductance of the solution if 2 platinum electrodes in solution are 2.1 centimeter apart and each having the area of cross section. Now they're asking you to calculate the equivalent conductance. In order to calculate the equivalent conductance, first we have to calculate the specific conductance. Specific conductance is given by the formula 1 by R into L by A. We learned it. The first problem I worked in this fashion only. I think. Resistance they have given us 50, 1 by 50 into length they have given us 2.1 and they have given the area to be 4.2. So 4.2, this is 1 and 2. So it will be 1 by 100, 1 by 100. Specific conductance is 1 by 100. The specific conductance, which is 1 by 100, can be written as 10 to the power minus 2. Correct? Now, what's that they're asking you to calculate? Equivalent conductance. How do I calculate equivalent conductance? It's given by the formula specific conductance into 1000 divided by normality. Specific conductance is 10 to the power minus 2 into 1000 divided by normality is 1. So we can write 10 to the power minus 2 into 10 to the power 3 divided by 1. So it'll be 10. So the answer for this question is 10. 10 equivalent conductance, Siemens centimeter square per equivalence. Siemens centimeter square per equivalence. So the answer for this question is 10. Did you follow?
Yes, sir.
Yes.
Yes, sir.
I'm finishing the class very fast, man. I was not able to type more number of questions. Anyways, we'll see. Which of the following have maximum molar conductivity? Which of the following have maximum molar conductivity? The first one is 0.08 molar solution, and its specific conductivity is 2 into 10 to the power minus 2 per ohm. The second one is 0.1 molar solution, and its resistivity is 50 ohm centimeter inverse. They're asking which one of the following has maximum molar conductivity. Maximum molar conductivity. In the first case, molar conductivity is mu, right? Mu is equal to specific conductance into 1000 divided by molarity. So specific conductance is 2 into 10 to the power minus 2. 10,000 divided by molarity is 0.08. So if you simplify this, you will get 250 ohm inverse centimeter square per mole. The first case. In the second case, we cannot calculate directly the equivalent conductance because they have not given you the specific conductivity here. So equivalent conductance is given by the formula specific conductance into 1000 divided by normality. You should remember specific conductance is equal to 1 by rho. Specific resistivity 1 by rho. So that is nothing but 1 by 50. So if you substitute here, it will be 1 by 50 into 1000 divided by normality is 0.1. So you'll get 200 ohm inverse centimeter square per equivalence. So they're asking which of the following have maximum molar conductivity. So maximum molar conductivity will be for the solution. 0.08 molar solution with specific conductivity. You can see the value is 250 here. Here the value is only 200. Followed? Students, did you follow?
Understood, sir.
Sir, are you there?
Oh, sorry. Call. Students are there?
Yes, sir.
Please make me a host, man. Now I'm a host here. Yeah. So call, you know.
Yes, sir. I made you the host, sir. Please continue.
The equivalent conductivity of sulfuric acid at infinite dilution is 384 ohm inverse centimeter square per equivalence. If 49 grams of sulfuric acid per liter is present in solution and specific resistance is 184 ohm, then calculate the degree of dissociation. Now, sulfuric acid, firstly, you have to calculate the equivalent of sulfuric acid. So equivalent weight of sulfuric acid is 49. You should remember equivalent weight of sulfuric acid is 49. They have given you 49 grams of sulfuric acid. So therefore, number of equivalents of sulfuric acid, equivalents of sulfuric acid will be equal to 49 divided by 49. That is 1. 1 gram equivalent it is called as. So they've given 49 grams of sulfuric acid. Equivalent weight of sulfuric acid is also 49. How do you find the equivalent weight of sulfuric acid? Equivalent weight of an acid is given by the formula molecular mass divided by basicity. Molecular mass of sulfuric acid is 98. Since sulfuric acid has 2 replaceable hydrogen, it's 98 divided by 2, it is 49. So that is how equivalent weight of sulfuric acid, we come to the conclusion saying it is 49. So 49 grams of sulfuric acid is 1 gram equivalent. That's why we get 49 divided by 40, weight in grams divided by equivalent mass gives you what? 1 gram equivalent. Now what is specific conductance here? Specific conductance will be equal to inverse of specific resistivity. That is nothing but 1 by 184. This is 18.4. It's not 184. It's 18.4. Specific conductivity is 1 by 18.4. Now we know that equivalent conductance can be calculated by the formula 1000 into K divided by normality. So it is 1000 into 1 by 18.4 divided by, what is the normality? They have not given any normality here, but they have given 49 grams of sulfuric acid per liter. 1 gram equivalent weight. 1 gram equivalent weight in 1 liter is nothing but 1 normal. 1 gram equivalent weight in 1 liter is nothing but 1 normal. So normality is taken as 1. So therefore, equivalent conductance, we will get it to be 55. Equivalent conductance, you get 55. Now, what is the question they've asked? They've asked the question, calculate the degree of dissociation. Degree of dissociation is given by the formula alpha is equal to conductance at a particular concentration divided by conductance at infinite dilution. At infinite dilution, you can see here, at infinite dilution, the conductance, what they have given is 384. So that therefore, the substitution will be 55. We found out the equivalent conductance to 55 divided by 384. So on simplification, you will get 0.14. That's nothing but 14%. So degree of dissociation in terms of percentage, it is 14. 0.14 into 100 is 14%. So hopefully you understood this problem.
Yes, sir.
Yeah. Others?
Yes, sir.
Yeah. The next one. The equivalent conductance of an infinitely dilute solution of ammonium chloride is 150. And the ionic conductance of OH minus and Cl minus ions are 198 and 76 respectively. What will be the equivalent conductance of the solution of ammonium hydroxide at infinite dilution? If the equivalent conductance of 0.01 normal solution of ammonium hydroxide is 9.6, what will be its degree of dissociation? So they have asked you, lambda naught of NH4Cl will be equal to lambda naught of NH4 plus lambda naught of Cl minus. So how do I, therefore we can write lambda naught of NH4 plus will be equal to lambda naught of NH4 Cl minus lambda naught of Cl minus. See, they have not given you directly the conductivity of ammonium ions. They have given you the conductivity of OH minus ions and Cl minus ions. So for conductivity of ammonium ions, if you take ammonium chloride, it's ammonium ions and chloride ions. If you subtract this value, you will get only what? Conductance of ammonium ions. If you take this value towards the left-hand side, this factor, if you take the left-hand side, becomes minus. So you get conductivity of ammonium ion. So that's nothing but 150. Conductivity of ammonium chloride is 150. 150 minus 109. What's the chloride ion? How much they've given? 76. 76. That will be 74. Likewise, now ammonium hydroxide, conductivity of ammonium hydroxide is equal to lambda naught of NH4 plus lambda naught of OH minus. So that will be equal to ammonium ion we found out is 74 and OH minus ion it is 198. So that will be equal to 272. This is lambda naught of ammonium hydroxide. So they are asking degree of dissociation. Alpha is equal to lambda naught, conductivity of a solution at a particular concentration divided by conductivity of a solution at infinite dilution. It is 9.6. They have given 9.6. 0.1 normal solution of ammonium hydroxide. Conductance they have given 9.6. Lambda naught is 272. This is at infinite dilution. 272. So we will get the answer to be 0.0353. Did you understand how do we work this problem?
Yes, sir.
Hello. Yes. The next question, how many cc's of chlorine will be deposited by 100 amperes current flowing for 5 hours through melted sodium chloride? How many cc's of chlorine will be deposited by 100 amperes current flowing for 5 hours through melted NaCl? They're asking how many cc's, centimeter cubes of chlorine will be deposited. We know that charge is equal to I into T. They have given current to be 100 and time they have given 5 hours. 5 hours as 60 minutes and each minute as 60 seconds. Time has to be taken in seconds. So therefore, it will be 18 into 10 to the power 5. It will be 18 into 10 to the power 5. The simplification, this value will be, charge will be 18 into 10 to the power 5. We know that W is equal to Z into I into T, or we can write W is equal to Z into Q. We just now calculated Q here. This is Faraday's first law. Now what is Z? Z is given by the formula equivalent mass divided by 96,500 into 18 into 10 to the power 5. That will be equal to 18E divided by 96,500 into 10 to the power 5. So on simplification, we will get 662.2 grams. So W weight will be 662.2 grams. So you should remember they're asking you how many cc's. So volume of 71 grams of chlorine at normal temperature and pressure occupies 22.4 liters. This is called as molar volume occupied by 1 mole of a gas. So chlorine atomic mass is 35.5. Since chlorine is Cl2, the molecular mass is 71 grams. So 71 grams of chlorine is 1 mole. Now, therefore, we can find 662.2 grams of chlorine will occupy what volume? It will be 662.2 into 22.4 divided by 71. It will be equal to 208.9 liters. The volume occupied by, or the amount of chlorine deposited is 208.9 liters. Followed this problem? Did you follow this problem?
Yes, sir.
Yeah.
Yes, sir.
You didn't ask me what is this E. E is the equivalent mass of chlorine. So I didn't mention it. It's 18 into 35.5 divided by 96,500 into 10 to the power 5. Equivalent mass of chlorine is 35.5 because valency of chlorine is 1. So atomic mass of chlorine divided by valency is equivalent mass. So it's 35.5. The next question. Right. The time required to coat a metal surface of 80 centimeters square with 0.005, it is 0.005 millimeters, 0.005 millimeters thick layer of silver. Density is 10.5 gram per centimeter cube. with the passage of 3 ampere current through silver nitrate solution is. They're asking you the time required to coat a metal surface of 80 centimeters square with 0.005 millimeters thick layer of silver. Density is 10.5 gram per centimeter cube with the passage of 3 ampere current through silver nitrate solution. So what is the volume of layer of silver? Volume of layer of silver is thickness they've given 0.005 into time that they given 80 centimeters. The area surface area is 80 into 10 to the power minus 1 into 80. Volume is 10 to the power minus 1 into 80. So you will get it. See, it's in millimeters. So converting into centimeters. So you will get it as 0.04 centimeter cube. Centimeter cube. Therefore, density is what? Mass by volume. Or we can write mass is equal to density into volume. Density they have given as 10.5. Volume we found out to be 0.04. That is 0.42 grams. Mass we found out to be 0.42 grams. Now they're asking the time required to coat a metal surface. Time required to coat. We know that W is equal to Z into I into T. Now we know that W is equal to equivalent mass divided by 96,500 into I into T. So what is T therefore? Therefore T will be equal to W into 96,500 divided by E into I. What is rate? 0.42 into 96,500. What's the equivalent mass of silver? Equivalent mass of silver, you should remember it's 108. And current, we are passing it for 3 amperes. So when you simplify this, we will get it as 125.09 seconds. Followed with this problem?
Yes, sir.
Another 2 problems I typed, and we'll work out that 2 problems and we'll try to solve. Stop. The same current is passed through solution of silver nitrate and copper salt connected in series. If the weight of silver deposited is 108, calculate the weight of copper. This problem is based on what? This problem is based on what? This problem is based on what law? I'm writing the formula. It's based on Faraday's first
Faraday's law.
So Faraday's second law. Faraday's second law. Now they're saying amount of silver deposited is 1.08. They're asking mass of copper deposited. Equivalent mass of silver we calculated, we found out it's 108. Equivalent weight of copper, it is 31.75. Atomic mass of copper is 63.5. So equivalent weight of copper will be equal to 63.5 divided by 2 because valency of copper is 2. So you 2 plus. Therefore, it is 31.75. So now what will be weight of copper? Weight of copper will be 1.08 into 31.75 divided by 108. On simplification, we will get the value to be 0.3175 grams. So weight of copper deposited is 0.3175 grams. Followed with this. Simple problem. This is based on Faraday's second.
Yes, sir.
Yeah. One more problem. 0.2864 grams of copper was deposited on passage of current of 0.5 amperes for 30 minutes through a solution of copper sulfate. What is the electrochemical equivalent? They are asking what is the electrochemical equivalent. So W is equal to Z into I into T. So Z will be what? W by IT. What is the weight? It is 0.2864. I is 0.5. The 30 minutes, 30 into 60, because time has to be taken in seconds. 30 into 60. On simplification, we will get the answer to be 0.0032 gram per coulomb. The electrochemical equivalent, the unit for electrochemical equivalent is gram per coulomb. All right. So the amount of, or the electrochemical equivalent is 0.0032 grams per coulomb. So this is the number of problems. We have worked more than 75, 80 problems. Not more than that we would have worked. So this ends the chapter electrochemistry. There are so many more questions to be solved. You can work on it from any of the material, and then if you have doubts, you can ask me. Or else maybe tomorrow also I will try to work some more problems on electrochemistry only. Few more problems we will try to work on electrochemistry. All right. Let's see. Just give me some time. Yeah. We'll work few problems tomorrow. Very less number of problems we'll work tomorrow. All right.
Yes, sir.
Tomorrow also we'll work. Maybe tomorrow I may not be in a position to type the questions. I will write the question and we will try to learn it possibly. If I get time, I will type. Otherwise, we will write the question and do it. So one more class I will require to work few more problems on electrochemistry. Different types of problem will work and then we'll try to complete it. All right. Madam, I'll stop the class now, ma'am. Ma'am?
Yes, sir.
Yeah.
Thank you, sir.
Tomorrow I'll continue with the same chapter, ma'am.
Okay, sir. Okay, sir.
Type the questions. I will write the question and
Thank you, sir.
bye.
Thank you, sir.
Bye then, Lakshmi. Bye.